Hey guys, I hope to start posting more problem solutions from my classes, and today we will be talking about classical mechanics, and I am doing some practice problems from chapter 10 as well as doing my homework assignment, and I thought this will be a playlist to start here on my channel. So the problem 10.1 is the one we will be covering today. Here is the problem statement, and let's get started on the solution. So the problem asks us to show the following. Oops. Okay, so we need to prove that the following sum equals to 0. That sum actually comes up in the derivation of the angular momentum, total angular momentum of a rigid body. So it will come in handy when we do that derivation, and this video will be the next one, or one of the next ones I'm planning to do. So it will be handy to have this problem solved before we do the derivation. And yeah, so if you imagine a rigid body being something like this, like a, I don't know, blob of matter, and we assume the center of mass is somewhere here, and the origin, say, is somewhere here, with respect to which we will be measuring all the distances. So the position vector of the center of mass is always denoted as the capital R. And suppose here we have our mass element dm. No, actually here it's just m alpha. We're considering just total elements of math. We're not integrating anything at this point. And so the position vector of this mass element with respect to the origin is denoted as r sub alpha. And the position vector of this mass element with respect to the center of mass here is r prime sub alpha. So this is our setup. And our task, so basically this this here is supposed to give you an idea what we're talking here about when we refer to those position vectors. Okay, so if we express this vector here in terms of the other two, we get the following. Okay, so like for me, it's always hard to do it right away on top of my head. So I do it actually a bit slow, but it works. So I know that this vector plus this vector always equals this. So that's how I do it, like the order of the vector addition. Okay, so from now, like from here, we can express the r sub alpha. And then we can use this expression here and sub this into here. So with this, our sum becomes the following. Okay, now we just distribute the sum. Or, well, we distribute the stuff under the sum. Okay, so this is how it works here. And now, since we also can distribute actually the summation sign here, we can do that too. Okay, oh, and by the way, I'm sure you're all aware that the summation sign here means that we're summing over alphas. We're just leaving this out here to keep it cleaner. And that's the same that the Taylor does too. Okay, so now let's look at this a bit closer. So if you look here, like under this sum, everything is dependent on the alpha. So we're summing over mass elements, and we're also summing over the position vectors of each mass element. So nothing can be taken out of the summation sign here. But in this term here, this r is independent of the summation variable, so it can be actually taken out. And that's what we're going to do. Okay. Okay, I'm sure all of this can be simplified quite a bit, but I mean, the steps can be made shorter, but I wanted to be extra explicit for like those of you who are not really, who cannot see it right away. At least I couldn't. The simplest problem took me some time. Not a whole lot of time, but actually it took me some of the reading and figuring things out. We should remember one thing, that the sum of all elements of the m sub alpha is just the total mass of this whole blob here. Yeah, of this whole thing here. So we keep that in mind, and also like we need to figure out what to do with that, with this, how to simplify that. If we recall the definition of the center of mass position vector, we can sort of see where we're going with this. Okay, so this is the actual definition of the discrete case of the center of mass, and another one would be, like, it doesn't belong here, but another one would be like this, would be the integral. Yeah, but that doesn't belong to this case, so we get rid of this, and then we continue. So this was like a side, and we can use that, right? Because if you look at this here and these are exactly the same. This and this are equal, like same stuff. And so we can safely say that this sum, I'm writing with a highlighter. Okay, so that's this sum equals r times m. And so if we take that, sub this into here, and rewrite that, we actually get what we want. And here you go, it's 0. That's it. That's how this problem is done.